Hello and welcome to yet another video of Cornerstones of Math. As for today's video, the problem itself is really simple, but it invokes some interesting discussions. At least that's what I think. So the problem itself is that we want to find this function fnx, or in other words, we want to carry out this summation. And this summation is the partial sum or finite sum of the first n terms of the geometric progression. So what would be the result of this summation? The theoretical background for this problem is really simple because there is a formula for the partial sum of geometric progression. The derivation of the formula is really simple as well, so let me quickly derive the formula for the partial sum of the geometric progression. The first term of the geometric progression is a, and the common ratio is r. The key idea to find this sum is that we multiply the common ratio r on both sides. Then we have r times the partial sum Sn is equal to, now this a becomes ar, so let's write it here. And this ar now becomes ar squared, and so on. So in the end, we have a r to the power of n minus 1, and we have additional a times r to the power of n. If we subtract the bottom one from the top one, we have 1 minus r times Sn is equal to, on the right hand side, the only term surviving is a and minus a r to the power of n. So 1 minus r Sn equals a times 1 minus r to the power of n. So if r is not equal to 1, then we can divide both sides with 1 minus r, which gives Sn equals a times 1 minus r to the power of n divided by 1 minus r. Here, it is beneficial to remember that this a refers to the first term in the partial sum, and this n refers to the total number of terms in the partial sum. Then you will have no problem applying this formula to various types of partial sums of geometric progressions. If r equals 1, then we cannot divide by 1 minus r here, so we must take a different approach. In this case, the partial sum simply becomes a plus a plus a plus so on plus a, and since we have n terms in total, this is equal to n times a. These are all we need in order to solve this problem. So now let's apply this formula to our function fnx. But before we apply any formulas, we must first deal with the fact that our function is defined using fractions, hence it is undefined at the point where the denominator becomes 0. Therefore, fnx is undefined at x equals negative 1. When x is not equal to negative 1, then we have the partial sum of the geometric progression. The geometric progression now has the first term 1 and the common ratio 1 over x plus 1. And here we must divide cases. When the common ratio is not 1, this means that 1 over x plus 1 is not equal to 1, that is, x is not equal to 0. In this case, we apply the partial sum formula, so we have the first term is 1 times 1 minus the common ratio 1 over x plus 1, and the number of terms is n. And this divided by 1 minus the common ratio 1 over x plus 1. This gives x plus 1 over x times 1 minus 1 over x plus 1 to the power of n. Next, when the common ratio 1 over x plus 1 is equal to 1, i.e. when x equals 0, then the summation becomes, which is really the value of fn0, which is just 1 plus 1 plus 1 plus so on. So it is just n. To summarize, fn x is equal to this when x is not equal to -1 or 0, and just n if x equals 0, and undefined at x equals -1. So we found the answer, but at this point I want you to think about other type of problems, the series or the infinite series. That is, the sum of infinitely many terms. Some of you may well know the formula for the geometric series, where the sum is given as the first term a divided by 1 minus the common ratio r. Using this, we can calculate the sum of this infinite series, which I will denote as just fx. The sum of this geometric series is first term 1 divided by 1 minus the common ratio 1 over x plus 1, so it is x plus 1 over x. But here, we do not divide cases according to the value of the common ratio. So why do we not divide cases for the series, but we do divide cases for the partial sum? Well, the answer is, you do divide cases here as well, but slightly differently compared to the partial sum. In the infinite series, the case division is that the sum converges to a over 1 minus r if the common ratio r is in between -1 and 1. And if the absolute value of the common ratio is greater than or equal to 1, then the series simply diverges. So our result for the geometric series fx is true only if the common ratio 1 over x plus 1's absolute value is less than 1, and the function diverges otherwise. If we compare this to the partial sum, you'll notice that our special case, the common ratio r equals to 1, is the diverging case in the infinite series, so we just happen to not care about that case if we are only dealing with converging cases. But you need to remember that in the partial sum, you must treat this r equals 1 case separately. And that's all for today's video. Thank you for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.